Thank you, Abhishek, for the kind introduction. Good afternoon, everyone. As he mentioned, the topic of my presentation today is lithography-free, fully printed lithium phosphate-based humidity sensors on paper as zero-waste sustainable electronic solution. So, before going to the slides, I would like to show you the outline. Motivation, how it goes is motivation, introduction and device fabrication, sensor performance, and summary. From the picture, you can see that we are seeing something very green, and what I have done is it's a green electronics. I mean, I have kept the theme as green color. So just to have a green future in our life ahead. You can see the problem now. What is the motivation here is these are huge electronic waste, what you can see in the left side. Just let me get there's a point here. Yeah. These are the electronic waste, solid electronic waste, what we are seeing. By WHO, what they have published recently, that this is the maximum this is the maximum solid waste what we are getting is electronic waste. And we do not have really a solution how to recycle and reuse them, because most of the problem comes from neurotoxins. One of them is lead. And last in 2022, 62 million tons of electronic waste were generated by the whole world, and you can see in different countries how they are generated from China, US, Japan, and our country is in the fourth. And you can see here that per capita how much we are generating waste. So as scientists, we need to find some solutions for that. So next, we try to find some solution. Now, before going to the solution, I would like to introduce Internet of Things. What it is, you must all know already by now. So there are four pillars of Internet of Things. First is the sensor, then the cloud, then the analytics, and excuse me. Please excuse me. So as I mentioned, there are four pillars of Internet of Things. What happens is we are connecting everything, all the devices via cloud, and then here the work is particularly about the sensor part. What we can make, which is a zero waste electronic device, which will be helpful to generate a sustainable solution to this problem what I just discussed. So now here you can see that there are different sensors they have used in this picture. For this work, I have chosen the humidity sensor. Now let's go to printed electronics. So what it gives the solution, the printed electronics, is that by using different printing techniques such as inkjet printing, screen printing, reverse offset printing, gravure, aerogel printing, 3D printing, what we can do is we can choose any substrate such as different PCBs, polymers, papers, textiles, and glass ceramics. We can print everything by just making the right ink for different printing techniques. Yeah. So here, this is the inkjet printing what we have used, and I'll show you the screen printer what we have used to prepare our devices. Yeah. Now, why printed electronics? I just mentioned that we can have a different substrate choice. We can print on anything. And then because the material will be conformal, and then we can get a device very easily on any substrate. So here, why printed electronics we have chosen is, you can see from this source that by this year end, the uses of sensors are still very less, because they are not optimized yet very well. So our work here is to find a solution in this direction, so that we can use more printed sensors, and then we can get rid of those electronic waste what I was just discussing about. So these are different printing techniques what you are seeing. Again, these are the pictures, and this is the paper on which we have prepared the whole design. And these are some conformal techniques, how you can see that these are some flexible substrates what people have used. Now, moving to why humidity sensors we have chosen, because you can see that humidity sensors are essential for different application fields such as food processing, medical and biomedical health monitoring devices, and aerospace, then structural health monitoring. So now let's move to the material what we have used. So to begin with, this is a revolutionizing material which has come in 2011 by Professor Yuri Gogossi group. And then what they have done is they have taken a max phase. Here you can see where max M stands for the transition metals, A stands for aluminum and gallium, and X stands for X stands for carbon and nitrogen. So what happens here is when you try to etch it out, what happens? These are some layer structure. If you see some particular direction, you try to in situ take out the material that is aluminum or gallium, and then you get kind of accordion-like structure, what you are seeing here. And then when you delaminate them, you get flakes, what you are seeing here. So now let's move to what we have done here. So in general, what you when you take titanium aluminum carbide and then try to etch them, you get this kind of structure as I mentioned previously. And then people generally take the supernatant of that as flakes, and then they use it, and rest of the sediment they throw it. It's just not usable because these are multi-layer, and they will create problem in printing, and also they will not give very high conductivity. And then there are various problems because the aluminum part doesn't etch out here. What we did is we took a paper substrate, we screen printed this sediment material, and then we prepared the electrode on the photo paper. So on top of that, what we did is we printed this sensing material. So what is the sensing material now? The sensing material is lithium phosphate. Generally, lithium phosphate is not dissolvable in water. So I will discuss about it, how it is dissolvable in water. What we did is we just reduced the pH of this solution. So from turbid, it became transparent. So what happens when you add certain acetic acid or something, some acidic media to that material, then it absorbs water and then forms a compound. I'll tell you later in the coming slides. So this is schematic of the device, how it looks generally. So the electrode material is this titanium carbide plus titanium aluminum carbide. And then next is the characterization of the material, the electrode material. So as you can see from the XRD, it is clearly visible that you have both the phases, not only the multi-layer titanium carbide, along with that titanium aluminum carbide also. So when we see it in SCM, I mean scanning electron microscopic, what we did is we saw that the accordion structure is present. To understand what are the bonds present here, what we have done is FTIR. There you can see OH hydroxyl groups, CH groups, and then Cl groups, CH groups are also present. When you see that under TM, you see this layer structure. To understand also the crystal structure, we have done SAED and then also HRT, where you see the crystals present there in hexagonal crystal symmetry. Now let's move to the characterization of lithium phosphate. You can see that in 110 direction, it's a preferential growth. And when you see that in ACM, what happens is you see it looks like a very homogeneous structure. But when you see in AFM, you see that these are particle structure. And then I will tell you next why these particle structures are important. So now next is FTIR, to understand whether it can absorb water in room temperature, where the humidity percentage was the relative humidity percent was 45%. There we see that OH group is still already there in the structure. So also you can find CH, C double bond C and OH CH groups are there. To confirm the bonding, we did XPS, and then we have found out the bonds present in the structure. These are POP, OP, and then the coordination, how it is. Now let's move to the sensor performance. Now this is the sensor. What it looks like is just the electrode, but we have printed the lithium phosphate on top of that with inkjet printing, because it's because the material was not compatible for screen printing, we decided to go for inkjet printing. Now, let's move to how the performance comes. So when you change the performance from 34 to various RH of relative humidity of the environment, you can see that the resistance of the material is going down, and then from one electrode to other electrode, the current is passing very well. All these things were measured at 1 volt. The plan is to make a self reliable. Yeah, 1 minute. Okay, I'll finish it. Yeah, self sustainable material. I mean the whole batch. So now what happens here is when you do some acetic media, that's what I was telling about, that you form lithium dihydrogen phosphate at the local level, which generally attracts the humidity, and then it allows for the resistance to go down from the interparticle electron transfer. Now you can see from this particle structure that what happens when you pass certain humidity, the chemisol hydroxyl gets absorbed. Then first fizzes out the layer of OH. Again, it forms a hydrogen bonding, and then from using that hydrogen bonding, you can the mechanism here is already proposed long time back by Grothus, and then this is called Grothus mechanism. What happens here is the hydronium ion goes from one water molecule to other water molecule, and then you can see from one electrode to another electrode how it passes. Now, everything was good. Now we needed to know whether it is repeatable or not. Well, it was for 20 cycles, there was no decrement in the performance. Now, whether it is flexible or not, well, the flexibility test also is passed. It was well performing. And then in that condition, we have also checked the repeatability. Now, the biodegradability study, whether the whole substrate is, the whole device is biodegradable or not. So from day 1 to day 14, we have checked that it is slowly degrading, and then we stopped the process there. I mean, if we would have continued, it looks like the material would have degraded properly and without disturbing the structure, growth of the saplings. Now, this is the summary slide where we have printed one humidity sensor, and then performance was pretty well. And then after 2 weeks, so we have also seen that degradation mechanism, and it's also performing very well when it is in bent condition. The strain was 2.5% in the structure. And then this is the mechanism, what it followed. And I would like to acknowledge IISc Bangalore and IIT for the work. And then thank you very much for your kind attention.